So until last week, basically what we have discussed is basically some kind of some basic ideas in terms of like how we can basically train either diffusion model or the flow model, and also how we can perform the generation process. And from this week until the next week, what we are going to do is that what we can do more with some kind of the pre-trained models. So as you would already know, actually there are some kind of some pre-trained the diffusion models, especially for the image video generation and also the video generation. And we are also seeing some kind of the many other diffusion flow models, not only for the images and the videos, for the many other things, like for some molecules, or I don't know, for the motions, or some kind of the robotics, the applications for the many other things. And these models are typically trained with some tones of the data. So we don't have some kind of the computing resources that we can really train those kind of models with the tones of the images for the videos, for example, right? But here the question is that with these kind of the pre-trained models, what can you do more? Can you just like get some kind of like typical images, or can you do some like many other things? So that's basically the topics that we are going to discuss for this week and the next week. This is basically the slide we have seen multiple times, right? So basically the advantage for the diffusion model were that it's basically achieve some kind of the better quality without basically losing the diversity, right? But the kind of the things, some kind of the downside for the diffusion model was basically the slow speed because of that kind of the iterative process. And what we have discussed so far was basically how we can accelerate this kind of the degenerative process through some kind of the Inference-Time techniques, which is basically changing some formulations in the generation process in a way that we can achieve some kind of the good results, even with some kind of few iterations, right? And we also briefly discussed some kind of the techniques that we can also accelerate the generation process through some kind of the fine tuning, right? So those are some kind of all the attempts in terms of like how we can basically run the generation process faster with the few number of the steps. But actually what we are going to discuss for today is that this kind of the iterative process actually can be useful in terms of like injecting some kind of the guidance. So what we have seen in the previous lecture is that the generation process of the diffusion and the flow model is all about making some kind of the trajectory, right? Starting from if we go back to the diffusion context, starting from the capital T and all the way going down to the zero, right? In the diffusion context, right? Then it's basically really making some kind of a trajectory starting from the standard Gaussian sample, x capital D, and then just like making the path in the space in a way that we are reaching to the x0, right? So it's all about basically making this kind of a path. But here, basically, what we are going to do is that we are every time when we basically make this kind of some paths, we are basically pushing those kind of points in a way that the trajectory becomes something that is reaching to the final point, which is something that we really want to see. Actually, we already have seen such kind of the case as an example. Do you remember what this was? Some kind of the cases that we are injecting some kind of the guidance in the generation process. No idea. Yeah, the classifier guidance and the classifier free guidance actually was the case that we are basically injecting some kind of the guidance. Basically, what we are doing is that it's all about basically computing predict the score and basically performing the reverse process based on the score information. And what we have seen last time for the classifier guidance is that given the condition, now we want to compute the score for the joint probability here, right? And the score for the joint probability, it could be decomposed into the marginal score here and also the likelihood score here. So it does the matter of like basically how we can compute the likelihood score here in some of that we are basically injecting some kind of some offset to some kind of each of these core functions here. And the idea for the classifier guidance was to basically train a kind of the classifier in terms of that we can compute this more explicitly by just training another kind of the additional neural network. And the idea for the classifier, the free guidance was to basically train a single network that can learn both the unconditional denoise and also the conditional noise as well, basically, which are corresponding to the marginal score here and also the likelihood score here. And we could also even control the strengths of the conditional noise in terms like how much we are going to push the kind of the intermediate data point over the trajectory in a way that we can control those kind of the passes. So that was kind of the basic idea that we discussed last time. But the thing is that these are all the cases that we need to basically train a kind of the additional neural net, or basically we are training the noise predictor with the pairs of the output that we want to see and also the noise here. So we need to basically have some kind of the training data in terms of the training the noise predictor. And what we are going to discuss for today is that how we can do this kind of the the injection of the guidance with some kind of the pre-trained the models without basically the training those kind of models from scratch with some kind of the conditioned information. So how we can do some kind of the test time kind of things in terms of basically adding some kind of the guidance. So more formally, we are going to try this, which is guiding our regenerative process at the inference time to make some kind of the realistic data point, which is basically something that we want to see, which is aligned with some kind of the specific the usual preference. So how we are going to do that at the test time is kind of the basic idea. And actually, diffusion in the flow model is really kind of the good framework for doing those kind of things. So as I said, for the GAN and the VAE, these are basically all the one-step model, right? For those kind of one-step models, it's really hard to basically add some kind of the guidance at the test time. But for those kind of the iterative process, as I said, we can basically control the kind of the either the velocity or the noise in a way that the trajectory that we are making is going to some kind of the target data point that we want to see. So there are some tons of actually the techniques for that. So I typically classify those kind of techniques into these 3D classes. Actually, there are more. There are many other kind of the things. So we are going to briefly talk about some kind of the very recent techniques in terms of like achieving this goal into these three categories. So actually, the first two are kind of the same. So you can see that actually the second one is kind of some special case of this coordinate manipulation. So for today, we are going to discuss like first these two things. And the next week, we're going to have some time to also discuss this one as well. So for the first these two things, the basic idea is that as we have seen for the classifier the guidance and also CFG case, we are doing some kind of the manipulation of the score. So every time when you perform the reverse process with the diffusion model, we are basically modifying this score term here in a way that becomes some kind of like the trajectory, making some kind of the output that we want to see. So there are actually quite many practical ideas in terms of this coordinate manipulation. So I'd like to just like show like one specific example here, but I also would like to emphasize that there are literally like tons of some kind of examples for that. And also there are many, some practical ideas, and some of those techniques are basically not explained with any kind of theory. So quite some practical ideas, but basically it works well in practice. And also many of those kind of techniques are basically developed, especially for the image and the video generation. And you can also consider applying those techniques for the other data modalities as well. So if I show like this specific example, which is called the repaint, this is the problem which is basically filling some kind of the missing regions in the images. So let's think about the case, and now we want to generate images, which is basically having this background region. So we basically want to fix these parts, and we only want to fill in this kind of the mask region. Then how we can make some kind of the image, which basically preserves this kind of the background region. And this is obviously kind of the problem of the generation, because there can be multiple the possible some kind of the ways to fill in this kind of foreground region, right? So if I show some examples here, for instance, if I erase this part and fill in some kind of the images here, there can be some multiple different kind of some expressions, the facial expressions like this, right? So this is really the generation process, the problem. Another very extreme example that we only have this part and we want to fill in the outer part. And then there can be even some cases that we are not even like making what's that? Some kind of some apple, it's not the apple. Some kind of fruit images, but something else, while still basically fixing this kind of this kind of the center region here. So you can see that this is basically some kind of a conditional problem, right? And we can consider basically training a diffusion model with this kind of the condition. If we already have some kind of the tones of some kind of the pairs of the input condition and the final the outputs, then you can obviously use some kind of the classify the guidance or the classify free guidance, whatever kind of things. So there are actually lots of the approaches to solve the same problem. But here, basically, the idea is that without basically training another diffusion model, what we are going to do is that we are going to use the pre-trained model to do this kind of the task. So the basic idea for this is that we are basically performing the denoising the process for the foreground region. So let's say this foreground region is basically the region that we are going to fill, and this background is basically the region that we want to basically preserve from the input. So here the basic idea is that how we can basically perform the denoising the process for the foreground region while basically also preserving this kind of background. And here the kind of the idea is that, so as I said, basically there is no theoretical explanation why this works. No theory here, just practical the idea. And you can try this yourself and see how much it works. So the basic idea is that, so each of the denoising steps, let's say we have the xt, right? So this is the intermediate, the noisy data point. And we perform the denoising one step in a way that we get the xt minus one, right? So this is the xt, and we perform the one denoising step and getting the xt minus one. And now what we want to do is that for the background region here, we also perform not the reverse process, but the forward process. So which basically means that we are performing the reverse process for the foreground region and the forward process for the background region with the same amount of the time step t minus one here, in a way that we are getting some kind of the two noisy data points. But one is coming from the reverse process, and the other one is coming from the forward process. So this one is basically having some kind of the information about the input, the background region here, because we perform the forward process. And this is kind of the output from the purely reverse process, the generative process. And what we do is that we combine these two. For the foreground region, obviously we take the information here, and for the background region, we take the information here. So we have basically here the idea is that we are having some kind of the two xt minus one here, the intermediate the data points, while basically the background region, the xt minus one is basically achieved by the performing the forward process from the background. For the foreground region, we are basically achieving the xt minus one by performing reverse process. So two xt minus one with the same amount of the noise, same level of the noise, but one is coming from the forward and one is coming from the reverse. And then combine this and then repeat this process. Then somehow this basically leads to basically getting some kind of the outputs, which is preserving the background region and also making the images in the foreground region, which is basically aligned with the background. So can you guess why this works? So here basically the thing is that it's pretty sure like why we are basically preserving the background region, right? Because every time we just like run the forward process from this like given the image, which means that if it goes to the end, the last step of the reverse process, what we are going to do is that we are just performing the forward the diffusion, like just like one step, probably out of the like 1,000 step, and also running the reverse process again based on that. So basically, which means that for the background region, the information that we are basically making here would be quite the same, almost the same from the input image, because we just like perform the foreground like one step and just like learning the noising again with just like one step out of the last of the steps, typically like 1,000 steps. So it's quite clear in terms of like why we are going to achieve some kind of the like, preserve the background region from the input images. Obviously, it is not very clear in terms of like how we can make this kind of like seamlessly like the connected images for the foreground, basically, but this kind of the combination of the xt-1 coming from the default process is giving some kind of the guidance in terms of that the xt should be going into the direction in a way that this like background should be should match the given the image. So for those kind of the techniques, the thing is that there's no theoretically guaranteed. And if you try yourself, actually there will be some failure cases as well. There are actually some cases that the foreground and the background basically do not match each other. So there are some kind of some engineering the techniques in terms of basically how we can achieve some kind of the better the outputs. But this is kind of like one sort of like example in terms of that how we can do some kind of the some score manipulation very practically in terms of that we can use some kind of the pre-trained model not only to make some kind of the full images, but just to fill in some kind of the missing regions. So there are many this kind of some interesting the examples. And also, especially for the image generation, what also people do is that typically when you design the noise prediction, the network, we're going to have some kind of the attention the modules, right? The cross attention and also the self attention the modules inside the noise prediction the network. For those kind of the cases, we can also do this coding manipulation by manipulating the attention maps in the self attention and the cross attention, the modules inside the noise prediction the network in a way that the score also becomes something that we want to get. There are also tons of the examples for that. But this is basically not the main topic for today, so I'm going to skip some details here. If you are more interested in some kind of those kind of practical techniques, I recommend you to check out the survey paper and also check out lots of the work here. These are all the kind of the techniques that are doing this kind of some score manipulation. So if I show some kind of more examples for that, what you can do by doing this kind of this score manipulation is that you can do something like this. So given this kind of the two images, like we are taking some structural information from this image, from this building, and also some style factor, the appearance information from this image in a way that we are making another image like this. So this all can be done basically doing some kind of like, doing some like the cross attention and also basically manipulating this core function based on the cross attention. This is also another example. This is actually work that we have done, which is basically not only making the image, which is not aligned with the given the text, but also basically aligning some kind of the objects in the image with the given the layout here. So what we can see here is that now we have some kind of some correspondence between some words here and also the 2D bounding boxes here. So which means that the car yellow here should be located on this yellow box. And also the green, the castle should be also located on the left, the green box here, and also the balloon as well. You can say that those objects are placed in the right region, given this kind of the additional some kind of the guidance information. And these are some kind of the other examples as well. And this kind of some kind of the arrangement of the objects in the images can be also achieved without like basically training on other diffusion models, but doing some kind of the manipulation of the score with the kind of pre-trained model. So this is actually quite interesting thing for the diffusion flow models. Through some kind of the iterative degeneration process, by just like somehow guiding some kind of the score function, actually we can do some kind of those kind of the manipulations and also the editing as well. And this is also the examples for the 3D, for the video as well. So this is the case that we have some kind of given the video like this. And by performing the inversion here, what we can do is that now we can regenerate the video while basically moving the object into the new the locations here. So those are also some examples doing some kind of the video editing using the pre-trained the video models as well. So there are lots of the examples for this. Oh, so more examples. Moving the base here to the new locations, and also moving the chairs as well. So this is basically the basic idea in terms of like how we can do some kind of the giving some kind of the inference time the guidance with the pre-trained models. And especially for the first category here, it's kind of good in terms of that we can give some kind of the very direct, some kind of the guidance by just like manipulating the scores. But obviously the downside for the first class of the technique is that first of all, there is no theoretical explanation. That's kind of the biggest problem. And also the second, these are all the techniques that are only applicable to some kind of some special cases, for especially for some spatial guidance, especially for the images. So you can also consider applying those kind of things for the other data modalities as well, but be careful in terms of that it does not guarantee to work. There can be some failure cases, and there's also no some kind of the explanation, the theoretical the explanation. So that's kind of the downside. So that's why we are going to discuss the second one, which is kind of some special case for the score manipulation, but with some kind of the more slightly more the specific cases, but for actually more the broader the applications, and also with some kind of some theoretical the explanations. So based on the second type of the technique, the typical types of the problem that we are going to solve is these like inverse problems. Is there anyone who has heard about inverse problems before? Inverse problem, I mean, it's very the common problems, right? So this is really the problem that we can see for many applications. So here the basic idea is that we want to basically find the causal factor X here. So this is basically what we want to find. The thing is that the only information that we have is basically the Y here. So let's say Y is kind of some partial observation, the partial information. And given the partial information, the thing is that we know how each of the data point X is basically mapped to the one of the partial observation Y here. So this function A is given. And the thing is that this function A may not be invertible, which means that given the partial observation, there can be some possible causal factors that would basically result in getting the Y here. And even there might be some kind of some noise, which is basically injected into the observation here. So what we know is that we know the function A here, and also the observation Y here. And given the observation the Y here, how can you get some kind of plausible the output X here? One of the plausible kind of the outputs. So as I said, typically this A function is basically not invertible, which means that there can be multiple possible X given the Y. So you can see that this is actually the conditionally generated problem, right? Basically, if you have some kind of the lots of the pairs of the X and the Y, then you can consider basically training another diffusion model using whatever like the classified frequency guidance or whatever kind of things in terms of that you just like really make a neural net that takes the Y as the input and making predicting the score that can produce the X, right? But here, obviously, what we are going to do is that how we can solve these inverse problems without collecting the training data set for those pairs, but only when you have the pre-trained model that can produce the X without the condition of the Y. So that's basically what we are going to do. Clear? Make sense? So again, this is the setup that we only have the observation Y here. And based on this, and also when we have the information for the function A here, we want to make one of the possible dx that would result in the observation dy here. And there can be some cases that we are having some kind of the noise, small noise into the partial observation where there's no noise. And there are lots of the applications of the inverse problems. Yeah, I just brought up some kind of the examples, especially for the image and the image domain, but also for the other data modalities, you can also find many of the inverse problems as well. So for example, let's see the Gaussian deblurring case. So this is the case that we are basically only having the blurred image here. And based on the blurred image, we want to find this kind of the clean image. That's basically what the smartphone does, right? For the images, right? So here, this is the case that this kind of the mapping function from the clean image into the blurred image is basically defined so we assume that this kind of the mapping is defined as kind of the convolution of the Gaussian corner. So in a way that the function A here is basically approximated. It's kind of the convolution of the Gaussian corner. And we only have some kind of the blurred the image. And given this kind of some blurry image, how we can make some kind of the clean the image, this one is basically the problem of the Gaussian deblurring. So this is basically one specific case. The other example might be super resolution. So let's say like we only have the low resolution the image. So from the low resolution image, how we can make some kind of the higher resolution the image. So this is also one of the inverse problem. Obviously, we know how we can do the downsampling from the higher resolution to the low resolution, right? This function is given. So this kind of downsampling the function is basically given. But we want to do the inversion in terms of that when you only have the low resolution the image, how we can generate some kind of the high resolution the image. So this is also one of the problems of the inverse problems, right? How about the in-painting? So this is exactly the same problem that we have seen for the repaint case. So repaint was the example that which is actually solving the inverse problem with some kind of some practical ideas like scolding manipulation. But this is actually really one of the case. We only have the background image, and the A function here is basically some masking function, right? We're just only taking some kind of region of the given the full image. So when you have some kind of some masking function, the A here, and the given the background image, how we can make some kind of the full image that will basically result in this background with some kind of the masking the function. Makes sense? And also, this is another example of the tomography, like some kind of CT scan or the MRI scan kind of things. What we do is that we only basically have some kind of the observations of the projection of some kind of 3D things here into the multiple views, right? So that's basically what we acquire through some kind of the MRI scan or some kind of CT scan kind of things, right? So when you have some kind of the multiple projections of the 3D things into the multiple views, from those kind of the 2D projections, how we can reconstruct the 3D is kind of the tomography the problem. And this is also the case that we know the projection function from some kind of the real things that we want to get here into the multiple 2D views. And we want to basically reconstruct 3D from the multiple projections. Also one of the examples of the inverse problems. Can you come up with some kind of the other inverse problems for not only for the images, for the other modalities as well? So actually, it can be kind of interesting some research problem if you can find some sort of some inverse problems for the other domain as well. I don't know for some molecule, for some other kind of things. There might be some cases that you have some kind of some partial observation, and you want to make some kind of the full output that is kind of aligned with this kind of the partial information. And those kind of the mapping function is already known. For those kind of cases, you can see that this is like one of the inverse problems, and then you can solve that problem using the technique that we are going to discuss here. So actually, there are lots of the applications. And as I said, obviously, the solution of the inverse problem would not be unique for many of the cases, for many kind of the typical the cases. When you solve the inverse problem, that's basically typically the case that the solution is basically not unique. So that's why basically we need to make some kind of either some conditional degenerate model, or we need to somehow leverage the pre-trained unconditional degenerate models while doing some kind of the conditional degeneration. So if we go into some more details in terms of like how we can solve the inverse problems with the pre-trained diffusion model. So what we are basically predicting using the pre-trained diffusion model is that we are predicting the score, right? We now know that the noise that we are predicting using the diffusion model is kind of like corresponding to this information, this score function. But now what we want to do is that we basically want to do some kind of a conditional degeneration, which means that now we want to compute the conditional score here. The score of the xt conditioned by the y. So given that we only have this information, how we can compute this? This is basically the problem that we are doing. And using the base rule, basically what we can see is that this part is basically the constant. So after basically computing the gradient of the log of the probability, actually what we can see is that actually this posterior this square conditioned by y is the same of the summation like these two. The score of the marginal distribution here, and also the score of this kind of like likelihood distribution. The score of the y conditioned by the xt. Is clear? So basically what we are going to see is that what we want to compute is basically this conditional score. The score of the xt conditioned by the y. But actually computing this conditional score is the same with this one from the base rule in terms of like basically this is already the information that we already know, right? So instead of like computing this conditional score, actually we can just compute this and like add this to the marginal score. So it's the matter of like whether we just directly compute this posterior score or the likelihood score here, adding this to the marginal score here. And the reason basically why we are seeing obviously this is that we're gonna see that actually computing this is like much easier than this. This is basically what we are going to do. Right? And also for the previous slide, we have seen some examples of like computing this, right? You should be familiar with like this score function. This is already we have seen in the previous slide. For the classifier, the guidance, or the classifier, the free guidance, we already have seen like how we compute this, right? So in the case of the classifier, the guidance, this likelihood score was computed from the pre-trained the classifier, right? So that was kind of the idea for the classifier, the guidance. For the classifier, the free guidance, we also jointly learned both the conditional and the unconditional scores using the same neural network. And this, the likelihood score was computed based on the noise that we are predicting, right? So these two were basically the examples that in terms of that we are computing this like likelihood score using another neural network by training another the classification network, or jointly learning the noise with the unconditional noise. So these are already some kind of examples. And obviously here, what we are going to do is that we are going to somehow, so the thing is that without some kind of the additional, some kind of training, there is no way to basically compute the accurate value of like this. What we are going to do is that we are going to do some kind of the approximation for this without any kind of the further the training in a way that we can do some kind of the inference time the guidance in the generation. So this is like basically all about how we are going to model this kind of the conditional score, the likelihood score without any kind of the training. For this, actually, I'm going to give some kind of the very basic ideas in terms of how we are basically approximating, how we are modeling this score. There are tons of the ideas for that. We are going to get into some easiest the ones first. So before we get into some more details for that, let's think about some kind of the easy case first. In terms of like, we are assuming that this mapping function, the A, is kind of a simple linear function. So this linear function basically means that the observation Y here can be achieved by multiplying some kind of the either some kind of matrix or something here into the clean data point X0 here. Actually, for many of the examples that we have seen in the previous slide, for the convolution or some kind of the super resolution for the masking, for the projection, for those cases, so all the applications, you can see that actually this A function becomes linear function. So actually, for many of the applications, actually the inverse problems that we are seeing is the inverse problems with the linear default model, linear functions here. So obviously there are some other cases that which is not linear. But if we basically assume that this function is the linear function, then now we can make it easier. basically what we can say is that given that this A is kind of linear function, now what we can say is that we can treat this condition Y here, the partial observation Y, as kind of the sample from the Gaussian distribution. Make sense? Since now this is kind of the linear function, what we can see is that this is the mean, and this is kind of the variance, the standard deviation for the Gaussian distribution. And now we know that when everything is basically the Gaussian distribution, then it becomes much easier, right? So that's kind of the purpose that we are making this as kind of linear function. So now we are basically modeling this as kind of the Gaussian distribution. Then what we can do is that since this is the Gaussian distribution, then we can now directly compute this conditional score. Basically, the meaning of like this score is that how likely we're gonna have the partial observation dy given the clean data point x0. Make sense? Okay, like the meaning of like this function would be is that how much we're gonna have this partial observation dy given this clean data point x0. But that, as you can see, the thing is that when you only have like this core function, there is no way that we can add some kind of the guidance in the intermediate steps of the generation process. What we want to do is that we are basically using this information to basically add some kind of the offset to this core in the intermediate steps in a way that we can basically bend the trajectory into some kind of output that we want to see. But based on this information, the only thing that we can do is that we can only compute this core function for the condition by the clean data point x0 here. But this is actually the score that we want to get. The clean data, the score for the y conditioned by the intermediate data point xt. Make sense? Okay. So basically, the thing is how we gonna basically approximate this. And do you remember the first test that we had last time? Actually, the problem 4 was basically about this, right? If you still remember the problem 4 of the first test, actually the problem 4 of the first test was like all about how we are going to do this kind of like solve these like inverse problems. And at that time, actually we did some very crude approximation. We assumed that this is the same. We did this. This is really bad approximation. So this is the simplest case. Obviously, the thing is that, as I said, there is no way that we can have some kind of the precise computation for this. We need to involve some kind of the approximation. But the worst approximation would be is that we just treat this is the same as we did this in a way that we can directly compute this from the formulation like this. But let's do slightly better the approximation. But also before that, you might already have some kind of feeling that this is now all about basically having this core function of the xt while we can compute this, right? So it seems like we need to see some kind of the connection between the xt and the x0, which means that this is also the place that the Tweedie's formula needs to comes in, right? So we are also going to use the Tweedie's formula here. So again, we have seen this like multiple times. Given the xt, we can compute the mean of the x0 conditioned by the xt, right? The expected value of the x0 given the xt. So this is like we have seen multiple times using the Tweedie's formula. But actually, the thing is that if we want to approximate this based on this information, what we want to have is that we need to actually know the exact distribution of the x0 conditioned by the xt. So we're gonna get into that point, how we can basically use that information in terms of like the conditional distribution of the x0 conditioned by the xt to compute this conditional score from this one. We're gonna see the connection between these two. But the thing is that basically we want to know how we can get some kind of the probability distribution of the x0 given the xt here. We only know the mean. We can compute the mean using the Tweedie's formula, but we don't know the full distribution. So we are going to do some kind of the really bad approximation in terms of that approximating this distribution again as kind of the Gaussian distribution. Again, this is really also the bad approximation. But this would be still better than this. Just making these two be the same. This is the kind of the worst case. Slightly the better version might be that we basically treat that this conditional distribution, the x0 conditioned by the xt, to be another, the Gaussian distribution with some kind of the arbitrary, some kind of the variance here. So we set some numbers here because we don't know this distribution. So it's kind of like really bad approximation, but we can only compute the mean value here using the Twiss formula, right? Makes sense? Then based on this, what can you do? Actually, we already discussed like what we can do. So do you remember this slide? This is almost the same this slide that we have seen in the lecture 5. If you go back to the slides of the lecture 5, then you're gonna see that actually there was a slide that looks like this. So this is basically all about basically how we can compute the marginal distribution here when both the prior and also the likelihood are basically the Gaussian distributions. So given that when the prior is the Gaussian and also the likelihood is like another the Gaussian defined in this way, then we could see that the marginal distribution dpy here could be derived into the another the Gaussian distribution. So that's basically why we was approximating everything as the Gaussian for the convenience to computing all those kind of things. So the thing is that now we know how we can compute the marginal distribution here, given these two, when these two are basically Gaussian distribution. Obviously, this is the time that you need to solve the quiz, right? So this is basically what we know from the inverse problem that we have when the a function here is basically defined as kind of the linear function. So our basically the assumption that this like the a function is linear is making us to have this kind of the Gaussian distribution here. And this is basically our approximation. We simply just approximated this conditional distribution, the x0 condition and the xt, as kind of the Gaussian distribution for simplicity. Obviously, as I said, this is really bad approximation. But the thing is that based on these two, now we can compute this. This is basically what we want to compute, right? Basically, the score function for this specific the conditional distribution, right? So based on the facts that we have seen in the previous slide, based on this, you can also download these slides on the course webpage or this slide. Download this and you can check out this. And based on this information, now let's consider computing this. So while you basically calculate this, so here basically the thing is that the more important thing than just like calculating all those kind of things is that we need to understand the meaning like computing this score like this. This score of like this conditionality distribution is basically some kind of the guidance that we are adding in the generation process. So we can basically imagine this kind of situation that we are seeing some kind of some journey of the xt, like starting from the x capital T, the time is basically decreasing from the capital T all the way to the 0, right? Starting from there, going to some like one of the points. So if we basically follow the given this score function, then whatever starting point that you have, this will basically go into the one of the some data point, the realistic data point, right? Having some kind of the journey from the x capital T, like going to the x0, right? So when you're making this kind of the path in the space, what we do is that we want to have some kind of a final output, which partial observation becomes exactly this y. We know basically how we can map the output into the partial observation through the given function, the a function here, right? What we want to get is that we want to get not just kind of any realistic data point, but it should be realistic. And also each partial observation should be this exactly y here. So in this way, while we make some kind of the path from the x capital T to the x0, what we do is that we add this amount of the score, the conditional score, which is basically pushing the intermediate point to go into some specific way. so that the output gets closer in a way that the output is aligned with the partial observation dy here. So how we are going to add this kind of some additional kind of the noise or the score to push the trajectory to get closer to the one of the data points which partial observation becomes the y here. The thing is that if we assume that the inverse problem is the linear the function, then we can compute this. The conditional score conditioned by the x0 has some the closed form, the analysis form. But this is not that helpful because actually we wanted to compute the score for the intermediate data point xt here. So that's the point that we need to make some kind of a connection between the xt and the x0 here. And this is the formulation how we are basically bridging these two in a way that we can compute the score like this from the condition of this condition by the x0. So we had that very crude approximation like this conditional distribution, the x0 condition by the xt. Obviously, this is really bad approximation. If this is really the Gaussian distribution, then why do we need to perform the reverse process? We can directly sample the x0 from the xt, right? There's no need to run the reverse process. So which doesn't make sense at all, right? So if this could be really approximated well with the Gaussian distribution, then we didn't need to run the reverse process. We can directly sample the x0 from the xt. So typically, this conditional distribution would be way more the complex distribution than the Gaussian distribution. But for now, without any kind of some further the 3D training or the fine tuning, there is no way to really compute this. So that's why we do this kind of some crude approximation. So which means that when you apply those kind of techniques, it does not guarantee to work for all the cases. But you can try this for the many applications and see how much it works. So basically, this formulation, we're gonna get this kind of the final Gaussian distribution for this likelihood distribution, the y conditioned by the xt. Did you get this formulation? So this is basically what we can compute with the formulation in the previous slide. And since this is the Gaussian distribution, now we can compute the gradient of the log of the probability with respect to the xt, right? The gradient with respect to xt, which means that if we take the chain rule here, then we all the way to the log of the things, then now we can compute the likelihood score into this form. Looks quite complicated, but actually this is not very complicated kind of things. We can compute this. And then so we get this. And here also one more thing is that for many of the cases, especially for the super resolution or some kind of the Gaussian, the deep blurring for many of the cases, there may not be some kind of the noise in the measurement. For example, like the downsampling is not involve any kind of some kind of noise, right? For many of the cases, we can assume that this sigma would be 0. Then the final likelihood score would be this one. Makes sense? So this is called pseudo-inverse guidance because of the fact that we need to basically compute the pseudo-inverse of the A here. And as I said, this formulation holds only when the inverse problem is defined as kind of linear function. Otherwise, we cannot compute the score, right? Okay. So you can really try this yourself. For the cases like when you have the known the A function, you can compute some kind of the additional offset of the score function here, and then see how much this will basically affect in the reverse process. So this is basically like one idea. The other kind of the idea is that we are really going back to that the even cruder the approximation. So what if we assume that this distribution is not simply the Gaussian distribution, but it's the Dirac delta the distribution like this. So this is basically the case that we have seen the first test. So in this kind of the very with some kind of very crude approximation, really bad approximation, the thing is that we can directly define this approximate this conditional distribution, the likelihood, the y condition with the xt, as kind of the Gaussian distribution like this. But as I said, this is really even worse the approximation. then what would be the reason for this? The reason why we are saying this is that this is obviously making even the computation even much simpler. So that's kind of the. So even with this kind of some much simpler the approximation. Now even we don't need to assume that this like the inverse function is a linear function, which means that with this kind of the even cruder the approximation, now we can cover the broader range of the applications, even when this kind of the A function is not linear function. Then what we can say is that the conditional score for this term, this distribution, can be directly computed in this way. So this was actually the answer for the first problem in the first test. So this is kind of good. Now we can compute the likelihood score as kind of the gradient of the L2 loss, L2 difference between the observation that we have and then basically the things that we are computing from the Tweedie's formula. So you can also see the meaning like this, right? The meaning of like this, the likelihood score is that we simply compare the given the observation and also the output that we compute from the Tweedie's formula here through the mapping here. So see how much these two is different. Compute the L2 loss and then take the gradient with respect to the xt. So that becomes some kind of the additional guidance that we are adding to the noise in the generation process. Okay. So yeah, this is kind of thing. So simply what we can do is that based on the really bad approximation, we simply take the gradient of the L2 difference between this is our reconstruction based on the Tweedie's formula, and this is the given the input. And this becomes the additional score. One more the additional thing is that if we go back to the DDPM, the formulation, so this is basically the things we have seen, like how we compute the xt minus 1 given the xt. So if we go back to this slide, we can actually see that this xt minus 1 the formulation is actually some kind of the affine function. Basically having some linear term here, multiplying something into the noise here, the prediction noise, plus some kind of some other terms here. Right? We can simplify in this way. Then what you can see is that let's say that this xt minus 1 the prime here, let's say this xt minus 1 prime with kind of the next sample, which is computed with the original noise here. So without any kind of some conditioning, this was something that we wanted to have, right? The xt minus 1 sample with the original score. But now the thing is that now we want to adjust the noise by adding this term, right? So here the thing is that when we have the next sample of the xt minus 1, let's say this is xt minus 1 the prime here, which is computed only with this noise. What's the kind of the next sample that can be sampled with this summation of the noise here? And what you can see is that if you already computed the xt minus 1 prime here with the original noise, so instead of like adding some kind of the noise in the noise prediction, here basically what you can see is that we can basically add this term into the next sample computed with the original noise to sample the new xt minus 1, which is now computed with the addition of the noise. Make sense? So the point is that instead of like updating your noise, we can do basically the update of the xt minus 1. It's basically the same thing. So in the DDPM formulation, basically what you can see is that either you can basically update the node here and compute all those kind of things. And this is exactly the same thing that we are basically computing the xt minus 1 first, and then updating the xt minus 1 with basically this amount. I mean, this is not any kind of some complex kind of things. You can just like write down all the things that you're going to say that whether you basically add some kind of the additional noise into the noise here, or basically adding this term into the xt minus 1, these two becomes the same. You can basically just derive yourself. nothing complicated. But from this basically what you can see is that these two are basically the same thing. And this is exactly the same generation process of the DDPM. For the guidance, what we need to do is that we are literally just like adding one line of the code in the PyTorch code by just adding just a single line. By literally just adding a single line in the PyTorch code, you can add some kind of the guidance in the generation process. So this is kind of the really interesting point. Adding the guidance at the test time, even without any kind of fine tuning, using the pre-trained diffusion model is such an easy thing. You just need to add like one single line into the code to give some kind of the guidance in the outputs. And based on that, you can solve many inverse problems. You can solve the super resolution in painting, whatever, deep learning, many other kind of things. Interesting. But obviously, this does not guarantee to make some kind of some desired outputs because as we have discussed in the previous slide, actually we introduced many kind of some bad approximations like this. Obviously, this is really the bad approximation. So because of the fact that there are many kind of the bad approximations that we are involving here, actually the final outputs may not be something that we want to see. They may not be really aligned with the partial observations. But actually some applications, actually this approach really works quite well. So we also have seen the two techniques for the in-painting, right? The first one was really basically doing some kind of a combination of these core terms using the repaint technique. And the other thing is basically just like using this technique, just adding this line in the code in terms of injecting the noise. Which one would work better? I'm just like showcasing explaining that there are multiple ways to achieve the test time, the guidance using the pre-trained models. You can try yourself and see which one is working better. Basically, there are multiple ways to do this kind of adding the guidance in the test time. And the idea that I introduced here was basically two very basic ideas. And there are 30 more ideas you can see in the many other places. So, and if I go back to the slide, actually the title that I had for this second class of the technique was basically the gradient descent from the future reward. But I didn't say anything about the reward here, right? And also here the question might be is that I explained all the things based on the DDPM deformulation that we discussed from the beginning of like this class. But what if we explain the same thing with the continuous deformulation, with the ODE and the SDE deformulation? Actually, we can also try to explain the same thing based on the ODE and the SDE deformulation. So we're gonna get into the point how the same thing, how this kind of the deformulation can be explained with the ODE and the SDE formulation next time. We're gonna also get into the point of the third one, the particle filtering, the next week. So as I said, there will be no lecture this Wednesday, and we're gonna continue the discussion for this second one and the third one the next Monday.